I'm happy to present Nadja Omanovic. All right, I got it. Nadja is a third-year PhD student from ETH-Zurich in Switzerland in Dr. Ulrike Ullmann's group. She holds a bachelor and master's degree from the same place in atmospheric sciences and the CLOUDLAB project, which is the title right there, which aims to study ice processes by conducting cloud seeding experiments in Switzerland. Her work includes being a drone pilot and modeling the field experiments. So that's a pretty interesting combination there. For this, she conducts large eddy simulations with the European weather model ICON to investigate ice growth processes in the model and how they can be improved with observational data from CLOUDLAB. So, go ahead.
I'm excited to be here. I just arrived last week and I'm staying here until end of June, so I'm really excited to be here and meet you all. So yeah, I'm taking this opportunity to introduce the CLOUDLAB project, which is a sole ETH project based in Switzerland, and you already see, and now my laser pointer is gone. There we go. You see our field site, it's a little bit in the middle of nowhere of Switzerland, and you see our most desired conditions that we have, a low stratus cloud cover, which is just gray and very depressing to work under. However, we did some exciting research, and I'm very excited to show it to you. As you see from the co-author list, this is a bigger project. We're quite a large team. We have 4 doctoral students with very different backgrounds. So I was always a modeler, and at the beginning of my PhD, I wasn't expecting to go into the field and become a drone pilot, so that was very exciting. We do have experience in the remote sensing and holographic imagery that I will show later a little bit more. So I'll start my talk with a general introduction to CLOUDLAB. What is it actually? What do we aim for? I'll talk also, given that I'm a drone pilot, I'll talk about the Meteor drones, which are actually our drones that we are employing for cloud seeding. And then we start going into actually our cloud seeding results based on the observations. This includes remote sensing and in situ observations. And then I'll conclude actually with my PhD project with the modeling in CLOUDLAB and how we try to bridge the gap between this very high resolution in situ measurements to a still bulk model. So here you see actually a picture of a low stratus cloud of our field site. We are somewhere beneath here. They look from above much nicer than they do from below. And I'll try to give you a short introduction. So all of you know, I mean, I'm here also in Sarah Tessendorf's group, what usually glaciogenic cloud seeding is used for. By injecting ice nucleating particles, we either aim for dissipating the cloud or we try to increase precipitation. Is this now snowfall or rainfall? However, the CLOUDLAB approach is slightly different. As I said before, we have a drone that flies into a supercooled cloud, and we go for these low stratus clouds that occur quite frequently in Switzerland and are more or less dynamically stable. And we release the seeding particles that should form ice, and they get advected towards our field site, where we have an extensive setup of remote sensing and in situ measurements. So this is what you saw before. The field site is the center, but with the drones, we are usually 2 to 3 kilometers away, so upwind of the field site. And combining all this, we actually tried to figure out what is the diffusional growth of ice crystals inside these clouds. How fast is it? And this we can use to compare to the models. So we're not aiming for precipitation enhancement or the dissipation of the cloud, but we're really aiming to study the ice processes inside this cloud. And then next here, this will play a video that you see how actually the flare is burning on the drone. So this was also the first big task to get the flare on a drone, and all of us were quite concerned to have a burning flare on a drone. Our burning place flares contain AGI. It's a mixture. They burn about 6 minutes. This is usually how long our seeding experiments are. So during our seeding experiments, we usually just ignited 1 flare, and this was enough to actually see what we want to see. What I already said before, so I'll give an overview why we have this low stratus. So this is a map of Switzerland, so Central Europe. This is our location. It's like 1.5 hours drive from Zurich. A little bit in the middle of nowhere. You see it's very idyllic, very Swiss when you want to. And what actually drives the low stratus is usually we have strong northeasterly winds coming in that push against the Alps, and you get a blockage. And the low stratus is also usually very strongly characterized by a very strong inversion. So it just caps it there, and it can live for several days. So we had up to 10 days of low stratus, which kind of allowed us to do repeated experiments. And we had 3 field campaigns, and I would say the first one was really a validation to try to figure out if this is even working. We had so much remote sensing instruments. We had the drones were new to us, so this was all a little bit much of testing. And only the last 2 years, and we just finished this year, the official field campaign time, where we actually did seeding experiments and this in a repeated manner. As said, this project wouldn't have been possible with other collaborators. Tropos from Germany is a big part that brought a lot of remote sensing instruments, and then we also had other universities who helped. So in the end, I think we have one of the biggest campaigns with 5 cloud radars coming in, and 2 microwave radiometers, 2 lidars. Most of the time, all of them worked, not always, but this is the usual. And this really allowed us to tackle this cloud seeding approach in the field. So on the next slide, I'll show a quick summary of the seeding experiments, and I go later into more detail. So what as I said, as the prevalent wind direction, we had mostly northeasterly, what we need for this low stratus cloud to exist. And we had wind speeds between 3 to 13 meters per second, so quite varying. And the wind speed is actually the one important thing that we need for ice crystal growth. Because I'm showing it here, binned by temperature. So in total, we have 74 seeding experiments. And what you see is the temperature range we do, or we managed to get. It wasn't as cold always in winter or in this low stratus as we wished. So we have a lot of them between -5 and -8 degrees Celsius. You see some of them a little bit warmer because the producers of the flares told us it should be already at -2 active. The material for seeding didn't really work, or it still needs to be evaluated, but usually we really saw a strong seal at -5. And then we see the growth times, and this of course depends on the wind speed and on the distance we were from the field. So we managed to get quite a broad range of different ice crystal growth regimes together. So to also give you a little bit of a glimpse what it was like to be a CLOUDLAB. So we usually had students over, so this was our motto to welcome to CLOUDLAB. They should just have fun and be curious. So they were visiting us every year to see the field site, to see what the remote sensing is doing. So we did a lot of work with them. Here's part of our team inflating the balloon. And you see it's starting to grow, and I'll get back to it later more. This is very simple. This is how we lived. These were our sleeping arrangements. So we were in an old military house that didn't have much, didn't really have a kitchen. So we were basically living off of camping, cooking plates, and had some mattresses. But it was fun. It was a big bonding experience with the whole team, that I can tell. Also here you see it's usually, chaotic. All of us tried to maximize layers because it's just really cold if you're for 3 hours outside. Our standard go-to food for lunch was noodle soup. This was the classic. And in the evenings, we tried at least to sit a little bit together and spend some time together if we were not in the field. And our closest supervisor was actually this cat who was the whole campaign with us. Always around, never too close, but always around, watching us. And in back, you see already the balloon. So I'll go in the next step to the meteor drones. And the meteor drones are developed in Switzerland by the company Meteormatics. And they're not made for cloud seeding at all. Their idea is that they actually do vertical profiles up to 6 kilometers. above sea level and to measure the atmosphere, so they get actually kind of a replacement or a substitute for radio sounds. And I'll show you how this usually looks like. This is a video they took where it's really boring. They just go up and down and measure the temperature, relative humidity, wind speed, and come down. And this can, in the end, be assimilated into operational weather forecasts. So this is it. I sped up the video a lot. So the drone, why we in the end actually chose it is because the biggest important thing was the de-icing capability. So we're flying into low stratus clouds that are super cooled. We get a lot of icing. And I'll show you a little bit more to that. So this is the biggest advantage of these drones that actually can do that. And Meteomatics spent a lot of time to customize. So one drone was specifically for the flares so that we can catch the flares and ignite them. And the second one was an aerosol measurement drone that had a portable optical particle counter at the bottom to measure the aerosols. So the idea of our in-cloud seeding, what we did, what I already mentioned a little bit before, is that we are upstream of our, in this case, here's the balloon, but basically this is our field site here. And we have the drone that does a zigzag pattern. By default, basically when we had the very first time a successful experiments, by default we had 4 times 400 meters legs, where it just went back and forth. It looks like it's moving also in the x direction. It doesn't. It just stays at the same spot and goes back and forth. And these particles then get advected, and we have this mixture of aerosols, ice crystals, and cloud droplets that go to the in situ instruments. As said, so yeah, we have a big, we had lots of icing. As drone pilots, so this was me, and my colleague and friend Anna, we're both drone pilots. These was usually very stressful times because we're flying beyond visual line of sight, so we don't see the drone, and we know it's probably just getting ice. And you see some examples. This is the sensor, the temperature and humidity sensor that is full of ice. This is usually after one flight, and this is 10 minutes inside the cloud. The motors fully ice. On the propellers, we see bits and pieces. And this is even though we have this de-icing capability. Otherwise, the drones would have already crashed before that. We wouldn't have managed to get the seeding done at all. And this kind of experience led to an interesting study for Anna, who's right now in review for the cold region science and technology, where she looked at this. So when we are in the field, we usually had a check on the battery current. And if you had no icing, it would just stay the same. But as soon as you start to get icing, you see that these slopes, that she also marked here in black, start to increase. And this was for us the indication that we have icing and that the battery consumption goes up as the power needs to be increased to remain with the flight speed. And then we initialize basically a heating. This puts it up here. It's on for 10 seconds, turns off, and then we ideally drop back to what we had before, slightly less. And this is basically how we did our flights. And this works, what said before, that the battery is like for 40 minutes, works if you don't have icing. If you're like doing this, then after 10, 15 minutes, you should be back with your drone, otherwise it will crash. And what she then continued doing is going based on this liquid water content measurements that we have on one side from in situ measurements and also from the remote sensing, and trying to figure out how well they correlate. And you see it's a really strong correlation. And the goal is basically, if these drones have this de-icing capability, to use this as a liquid water content measurement indirectly. Yes, this is a small excursion. And here are a few more pictures, kind of nice ice formation. This was on the rope of the balloon. This is the instrument after 3 hours of experiments. On the balloon, they can stay up much longer. We got a thick layer of rimed ice on top of it. Here, they basically started de-icing the rope, and in the end, they had a huge pile of just ice on the ground. And this is where our fence, after a week being inside the low stratus cloud. So quite extreme conditions sometimes that we experienced. So going now into the seeding signal and our cloud seeding approach within the observation. So these are the radars, you see some of them here, and the balloon back there. And I'll start with the remote sensing. So what I'm showing you here is from a vertically pointing radar at the field site that measures the radar reflectivity and across the height. So, and I'm showing you the 3 stars, which were basically the starting times of the experiments, and this was upwind, so we were a distance away from the seeding, and we always see very clearly an increase in the radar reflectivity every time we see that. So this was one of the first experiments where we thought, okay, it does work with our baby flare of 200 grams. We do see something. In addition, what we did with these 3 experiments is that we varied the distance. So the first one was 2.5 kilometers away from the field, and then 2 and 3 kilometers. And we do see, and I hope you also can somehow see it on the projector, that, for example, the furthest distance has also the strongest radar reflectivity. So we do see an impact on the ice crystal growth and on their sizes. So that they must have been larger than the others. So I said we had so many radars. This also meant that with one radar, we did a sector scan during the experiments. So basically just doing downstream the pattern going back and forth like this. And I'll show you, and this should start playing. And you see it's a background cloud, and here comes the seeding plume with a very strong and clear signal. And then it disappears again, and the background cloud is back in. So this was very exciting for us. And then the next step was actually that we also, so what you saw before, these instruments on the balloon are quite localized. So this is about this size, and all of us were scared that we actually never will hit that balloon with our measurements. But this is basically for the same experiment, and you see these are the holographic images, so coming in, and all the dots are basically ice crystals that are flying by and then disappear again. And this is really where the in situ measurement helps us a lot. So as said, we have this big balloon. We attached the instruments down here. So one is our HOLIMO, which is our holographic imager. We had a POPS on it, which is an aerosol measurement. We had a sonic and radio sound. And it's operated from this wind shear to give rope and to get actually the balloon back in. So now, what you saw before, the radar reflectivity is nothing new, but I added now the ice crystal number concentrations to it. In per cubic centimeters, if you're more used per liters, just multiply by 1,000, and the aerosol concentration. What we see, it's the same time axis. They are really nicely co-located. So every time we see an increase in radar reflectivity, we do see an increase in ice crystal number concentration, but we also see an increase in aerosol, meaning not all of the aerosol that is actually in these flares has been activated or nucleated into ice. If you're wondering what's happening down here, this is just when the balloon basically came back into the boundary layer and then in a more polluted environment. So here are some snapshots of ice crystals. We have pretty nice hollow columns, for example, pristine ice, but we were also surprised that we actually already after a few minutes can see aggregation at this rate, and they're quite large. So based on HOLIMO data, we can now actually start working on this ice crystal growth. And now for this, we have these 3 experiments, what I showed you before, these 3 different distances. So the dark red has the longest growth behind it, and I'm showing you here the size distributions of the different ice crystals. And we clearly can see with increasing the distance, we also increase the mean ice crystal from the major diameter. So this was the first time where we see, okay, we can, by adapting this in natural conditions even, we managed to get some sensitivity study out of that. And the next thing is that we're looking, of course, we're in a mixed phase cloud, so the Wegener-Bergeron-Findeisen process is at play. And I'm showing the same 3 experiments. And we can first, on the left axis, you see the liquid water content and the cloud droplet concentration, and the right axis, the ice water content and the ice crystal concentration. And we'll just first look at the background liquid phase for these 3 experiments, and we can say they're pretty similar. So this repeatability is a well enough assumption that we can just redo the experiments over and over. So now so one color, what you see now is that we have here for the liquid phase, and then the ice crystal concentrations and content are in the orange shades. And what you see is for the shortened distance, first of all, for all of them, we have a decrease in the liquid phase, and this pretty drastically. So clearly that the liquid phase gets reduced when we have the ice crystal present, so that we really can observe the Wegener-Bergeron-Findeisen process. What we also see is while the ice crystal number concentration drastically decreases with distance, we keep the same ice water content. So basically just meaning less ice crystal aggregated together, forming bigger aggregates. So this is really to show that we do have significant reduction in the liquid phase, also in situ measurements that highlight our Wegener-Bergeron-Findeisen process. So now this has been an overview of CLOUDLAB, and there's been lots of different research ongoing, and my colleagues are also working on that, and there will be more papers on that to follow. I will now focus more on my research, which has been the modeling. What you see here is a simple 3D animation of the seeding plume, the ice crystal number concentration, on top of topography from the model. And I'll walk you through it, what we did. So the first step was actually to implement a seeding parameterization into the ICON in the large eddy mode. So in this case, we use a resolution of 130 meters. And with the two-moment microphysics, of course. And here you see the parameterization that we introduced into the model. And you see this strong dependence of silver iodide on temperature. So basically, it starts at -5 and then increases very fast. For seeding inside the model, what we did is we tried to mimic as closely as possible the field setup. So here's our field site. The triangles is the native model grid from the ICON. So that's an icosahedral grid behind it. And we said we tried to mimic also these 400-meter legs we had before. And we just filled 3 grid boxes, basically, with 10 to the 6 seeding particles. I'll get back to this. This is an unknown number for us. We had to tune a bit to get to this number, but I'll talk about it later a little bit more. So once we had this in, we did the first seeding experiments and tried and compared it to the observations. And here you see one of the radar scans, and this is an elevation scan, just vertically going back and forth, and the model at the same time. And we were quite happy, or I think at the beginning of my PhD, I was pessimistic if the model can ever really catch up with the observations, but I was quite happy to see that we actually have a good qualitative match. And the nice thing now, of course, about the modeling is that we can track the whole plume. So what we had is that every 5 minutes, we had model output, and then we can track the whole plume. And this looks like this. So the colors both show ice crystal number concentration. It's just more for better visibility between the different time steps. So just every 5 minutes, one time step. And we nicely see how the plume, in the beginning, especially here in the cross-section of the plume, you see with very high concentration, the plume starts descending, aggregating, sedimenting, and disappears. So now we can also look a bit in the 3D animated view. So this is the topography that we have. Then our very nice low stratus clouds, which we're all very happy to get, because usually the models struggle very hard to get this in a fog layer and to be persistent. So I'll just remove it for better visibility. And now what you see is basically every minute one output of the plume. I should start here. How the ice crystals are basically forming, and the brighter the color is, the higher the concentration, and how it spreads out in all dimensions and then basically disappears. So we were very happy that we managed to get this done. This was basically the first proof of concept. Now I talked a lot about the in situ, and measurements, and these are the ones that actually are quite exciting for us. So what I'm showing you here is from one experiment, the ice crystal number concentration, which you already saw before for different ones. And what we did, and this is now, we basically tuned the model to the ice crystal number concentration observed, because we didn't know, or we still don't know, what the aerosol concentration is. So we don't know how many particles per second per cubic meter are emitted from these flares. So to circumvent that, we said, okay, we just go for the ice crystal number concentration, and if they match, then we can go a step further and look more into the Wegener-Bergeron-Findeisen process. And this is actually what we did. So yeah, we have the ice crystal number concentration. At the top, I now show also the cloud droplet number concentration. And you see, we do have some variation, and also with some high ice crystal number concentration, we do have really strong decreases in the liquid phase. And to quantify this, we defined basically a median cloud droplet number concentration of 20 minutes of the unperturbed cloud, and said everything that is below this median and at the same time has ice crystals present in the volume will count towards the direct interactions between those two phases. And this basically, the brown lines are going into it, what we then call the cloud droplet reduction. And you can focus first on the brown color, so this is what the observations do. And the green dashed line is what the model does. And this is for one experiment shown here. I did this for several sitting experiments, and it's pretty similar, sometimes even more drastic. In the model, we just don't get to the point that we can have these strong reductions at the same time as, like timing-wise, as we have in the observations. Only, like, for example, 10 minutes later, the model starts to catch up and get to this ice crystal. These cloud droplet reductions. So in our case, our setup as it is, it appears that the model is too slow in reducing the liquid phase. We can also look at this differently based on the equivalent ice crystal radius and the cloud droplet radius. So this is now every 5 minutes time step, which you saw before with the colorful plot. And we start off after seeding, and then it goes over time. And we see that the ice crystals do grow. They get bigger, and they start sedimenting. And we also see that the cloud droplets get smaller over time. But now if we compare with the in situ observations, we see while the cloud droplets agree very well in their cloud droplet radius, we do have a bigger mismatch between the ice crystal, the equivalent ice crystal radius, modeled and observed. So this is kind of the first study. I've been continuing working on that because there are now lots of open questions how you can improve that. I'm happy to discuss them afterwards. I'll just wrap it up now. So first of all, yeah, our CLOUDLAB approach works. We were all really surprised, I think, and happy to see that based on, basically using glaciogenic seeding to investigate a very specific cloud microphysics process. We also see that we can kind of do lab experiments in the field by adjusting the seeding distance, or also with the wind speed, and to infer more about the ice crystal growth. And we did see that in our case, that the model is not really able to represent what we see out in the field. And with that, I thank you for your attention. I'm looking forward for your questions.
Okay, great. Questions? I see Greg.
That's really fun stuff. I really love the combination of a de-icing drone and all this ice crystal growth. My one thought is your ice nucleation parameterization seems to just be a pretty simple sigmoid function that starts off pretty not quite warm enough, if it seems. If you're having troubles getting enough growth and decrease of liquid, see, it really still has incredibly low fraction at -8. So why not just slide that to the right, so to speak?
Absolutely. Yeah, you can do that as well. At the moment, this is based on lab measurements, the thing. We're trying to get from the field experiments in ice nucleation rate out of it so that we can actually fit the parameterization to it. But yes, this is one sense, and this would fix it. That is true. There's also, we could introduce more particles. That is also one option. Yeah, that's absolutely true.
Give me exercise today.
Thank you. Great talk. Thanks a lot. Another explanation for the model being too slow is for the WBF process to get going, you need to bring the droplets and the crystals together very closely. So it could be a resolution issue.
Same, yeah. So in the meantime, when I was doing the study, we were stuck with 130 meters for numerical issues. We managed to get to 65. It gets worse with 60.
I mean, very, very closely. I mean, if,
Yeah, that's also a reason why I'm here.
yeah, so it's not probably way beyond the resolutions you have at hand for the model.
Yeah, absolutely. No, it would be a DNS would be very interesting to see.
Yeah, it's not possible in that framework, but maybe this is a thing that needs to be parameterized on top of what you have in the LAM, in the cloud physics package there, I
yes,
guess.
that could vary. Yeah, I think the turbulence is a big issue in this case.
Thank you. Very interesting. One of the questions I had was the length of time that your power technique is putting out particles is 6 minutes. And yet I understood you were looking over a time period of maybe 15 minutes for growth. So how do you account for the fact that you're nucleating particles over a 6 minute time period, but you're only looking at a time period that's relatively small time compared to nucleation? Do you understand?
So you mean that they nucleate, so we emit particles 6 minutes, but we only measure them like 10 minutes later? Or I'm not sure if I fully understood the question.
Well, you're nucleating particles potentially over a 6 minute time period, and yet you're looking downwind, maybe 15 minutes later. But some of the particles you're looking at could have nucleated at 15 minutes or 15 minus 6.
Yes, yeah. So we do, of course, have the assumption that we have immediate nucleation, and it's starting as soon as they're emitted. What we are combining is when we combine it basically when we have the in situ measurements, which is up to 10 minutes later from the seeding start, and this is the same for the model. But it is an assumption, and probably not so wrong. We did some long wind scans that I didn't show, and they're very much preliminary, but we do see a change in radar reflectivity very early on from the seeding phase. So we do assume that the ones that can nucleate, and which is a very small fraction, like 1% of all aerosols emitted, nucleate immediately.
Yeah. Another question I had was with regard to aggregation. Now, you said you observed aggregation, and are you including that in the model for trying to look at both the number of particles that you see as well as the size?
Yes, yeah, we do. So I did both ways of analysis. So we do have aggregation in the model. I also turned off aggregation in the model to just look at the pristine, and it looks very much similar. We can do the same for the in situ. We can differentiate between in situ particles and rimed or aggregated particles.
Yeah. We did a seeding experiment back a long time ago in Colorado over the mountains, where we used a sailplane to spiral up and hover inside the cloud. And then we released seeding material below in a certain point. And we found that as we studied this cloud, that you'd have a maximum number of ice particles which would begin to fall off because of the aggregation. So you reached a maximum number of ice crystals. I'm curious, do you see something like that here?
I'm just trying to think of all our measurements.
This is too detailed.
We can
Perhaps
discuss
I'll
later.
talk to you later.
Yeah.
Thank you.
Thanks.
What sort of vertical motions are there in the cloud before and after seeding? And is the latent heat release a significant driver of moisture into the layer?
Very good question. So I'm pulling up this picture again to kind of show you a little bit the topography around it. So the wind is coming from this side if we have northeasterly wind, and we notice that the wind gets pushed up because it goes up to the hill. We're kind of exposed. So we do see some dynamic invigoration. We have one case which is discussed in the BAMS paper that was last year published, where we do think that we have also an invigoration from latent heat release. It is just very difficult to quantify it. Even though we say this low stratus cloud is quite dynamically stable, it's not. It is quite turbulent inside. Also kind of connected to our aggregate question, we often saw pristine ice crystals arriving at one time, and then 10 seconds later, a whole batch of aggregates, kind of pointing that probably these aggregates did some different pattern throughout the cloud. So this is quite turbulent, and it's quite difficult to disentangle.
Yeah. Well, one thing you could do is release chaff at the same time, radar chaff, at the same time or after seeding, just to see what the vertical motions are like.
I think that is for CLOUDLAB 2.0 planned. We noticed this after our campaigns. That's a good point, thank you.
Yeah, thank you, Nadja, for the great presentation. I do have a question on the HOLIMO, I think the hologram observation. So what is the smallest size you can detect and confirm that's ice?
25 microns.
25 microns.
Diameter. So they always talk in diameter. 12.5 in radius.
So you can actually distinguish the liquid phase from the ice phase at that resolution?
At that, yes.
Okay.
And this year, for a few days, so one of the PhDs actually built a new instrument that goes down to 3 microns in radius.
Okay, that is...
And this is a little bit of a game changer that we also see now, the lower distribution of the cloud droplets and ice crystals. But this is very much preliminary, and he just started the analysis, basically.
Well, let us know. We definitely want some capabilities like that. But that actually, my question related to how you parameterize your ice formation. And so in your model comparison to the observation, do you also compare just the same size range, or just the ice category in your model being actually?
I gave the whole ice category.
Okay. That might explain some of the differences in terms of the supercooled liquid consumption rates. But also, I'm wondering, do you have any idea why you increase your spatial resolution but gets worse comparison in terms of the liquid depletion? I just wonder what's in your mind right now.
Not yet. I was also really surprised, because thinking if we resolve more turbulence, we'll get a little bit better, but we're really worse off. It's a little bit difficult to disentangle at the moment, because it was also a full model version change to get to a stable 65 meters. So lots of things happened in the model, and I can't really tell at the moment, no.
Well, I also suspect microphysics might have, in the code of microphysics, might have something to do with it. So,
Yeah, I wanted to follow up on Lynn's question with that. How is vapor growth actually treated in the model? Because you showed in the pictures things like, it looked like hollowed columns, things like that, where you might be getting growth at a fairly low deposition density, leading to accelerated growth, say, compared to the high deposition density sphere. So I'm wondering if some of the delayed depletion of liquid might be related to just the treatment of vapor growth in the model.
So it's the classical one. So basically, you assume some oblate spheroid with the ventilation coefficient and the capacitance. I did the tests on that. And of course, if you increase the ventilation, you will speed up your growth and you get a better match. However, I calculated with some assumptions the ventilation and the coefficient and capacitance from the in situ data. There's some assumptions to that. And it agrees pretty well what the model already does. So while we see that there is a mismatch and that you can play around with the vapor deposition, I'm not sure how much we'll get from it.
Some of that, and I'm kind of looking over here at Jerry, might be just the breakdown of the capacitance model and how it works for this kind of growth, especially for these small kind of hollowed out particles.
Yeah, that's yeah.
We could talk.
We can
talk
talk.
offline.
Yeah, that would
maybe
be
too.
interesting, yeah.
I'd be curious.
Thank you. That's an interesting talk. A couple things come to mind. First of all, it's kind of neat that you've been able to go and put the drones in the cloud, which has always been a challenge for folks to do that without visual sighting. Be interesting to know how if we can do that over in this country.
You do.
But
They have a station in North Dakota that does that now.
okay, good. The other question, a couple of things. One is, and maybe some of the folks here that memory is better than mine, but it seems like a lot of the silver iodide smokes acted by contact nucleation. And I was wondering, do you have that in the model? Or do
So
you?
we're actually assuming, so we have a big mixture in this flare, and the lab measurements show it's super hygroscopic. So we rather go over immersion freezing.
Okay. And is that the mechanism
This
in
is
the
the
model?
mechanism we have in the model, so it's limited by the cloud droplet number concentration in the cloud.
Okay, and then it's probably not a factor because of the small size of but do these drones make APIPs at all?
What do they make?
Do they produce ice by themselves?
No, yeah, no, they don't. No, we checked, we did several tests, also the downwash of the drone, how it impacts the aerosol coagulation. It's negligible.
Thanks.
Okay. If there's no further questions, let's thank the speaker once more.
Thank you.